a central flexible axis, a true chorda dorsalis analogous to that of vertebrates, pages 278 to 9. This point of view is strengthened by the fact that in Malgala, studied by Lacazzi-Duthiers, the embryo is practically stationary, and forms no notochord, nor ever develops sense organs in the cerebral vesicle. Jard's general conclusion is that the true homology with vertebrates ceases after the formation of the cavity of Rusconi and the medullary groove. The homologies established by Kovalevsky for the notochord and the relations of the digestive tube and nervous systems are not atavistic, but adaptive, homologies, p. 282. There is accordingly no close genetic relationship between ascidians and vertebrates. Jard's criticisms did not avail to check the vogue of the new theory, which soon became an accepted article of faith in most morphological circles. 397 The fall of the ascidians from their larval high estate provided the text for many a Darwinian sermon. Some years after the genetic relationship of ascidians and vertebrates had been established, a rival theory of the origin of vertebrates made its appearance, a theory which was practically a rehabilitation in a somewhat altered form of the old Geoffroyan conception that vertebrates are arthropods walking on their backs. This was the so-called annelid theory of Dorn and Semper. Both Dorn and Semper started out from the fact that annelids and vertebrates are alike segmented animals, and it was an essential part of their theory that this resemblance was due to descent from a common segmented ancestor. Both laid great stress on the fact that the main organs in vertebrates are arranged in the same way as in an annelid lying on its back, the nervous system being uppermost, the alimentary system coming next, and below this the vascular. Dorn's earlier views are contained in the fascinating little book published in 1875, which bears the title Der Ursprung der Wirbeltiere und das Prinzip der Funktionswechsel, Leipzig. He followed this up by a long series of studies on vertebrate anatomy and embryology 398, in which he modified his views in certain details. We shall confine our attention to the first sketch of his theory. If the vertebrate is conceived to have evolved from a primitive annelid which took to creeping or swimming ventral surface uppermost, a difficulty at once arises with regard to the relative positions of the brain and the mouth. In vertebrates the brain, like the rest of the nervous system, is dorsal to the mouth and the alimentary canal. In an inverted annelid, however, the brain is ventral to the mouth and is connected with the dorsal nerve cord by commissures passing round the esophagus. It would seem, therefore, that the primitive vertebrate must have acquired either a new brain or a new mouth. Dorn took the latter view. He supposed that the original mouth of the primitive ancestor lay between the crura cerebelli in the fossa rhomboidea, and that in vertebrates this mouth has been replaced functionally by a new ventrally placed mouth, formed by the medial coalescence of a pair of gill slits. 399 Probably the two mouths at one period coexisted, and the older one was ousted by the growing functional importance of the newer mouth. The gill slits were considered by Dorn to be derived from the segmental organs of annelids, which were present originally in every segment of the primitive ancestor. The gills were at first external, like the gills of many chetopods at the present day. For their support, cartilaginous gill arches naturally arose in the body wall, and the superficial musculature became attached to these bars. There existed in all the segments of the annelid ancestors of vertebrates gills with cartilaginous skeleton and gill arches in the body wall. Each gill had its veins and arteries, each had its branch of the ventral nerve cord, and between each successive pair of gills a segmental organ opened to the exterior, p. 14, 1875. The paired fins and limbs of the vertebrate arose by the functional transformation of two pairs of these gills. The anterior gills became the definitive internal gills of the vertebrate, for they gradually shifted into the mouths of the anterior segmental organs, which had already acquired an opening into the pharynx and had been transformed into true gill slits. The posterior gills degenerated and disappeared, but their arches remained as ribs. Gill arches and ribs were accordingly homologous structures and formed a parietal skeleton. The vertebrate anus, like the mouth, was probably secondary and formed from a pair of gill slits, the postanal gut of vertebrate embryos hinting that the original anus was terminal as in annelids. The unpaired fins of fish were originally paired and possibly arose from the coalescence of rows of parapodia. Dorn assumed also that the primitive annelid ancestor must have possessed a notochord to give support in swimming. If vertebrates arose from primitive annelid ancestors, how account for Amphioxus and the ascidians, which seem to be the most primitive living vertebrates and yet show no particular annelidin affinities? Dorn tries to answer this awkward question by showing that these forms are not primitive but degenerate. He points out first that cyclostomes are degenerate fish, half specialized and half degraded in adaptation to a parasitic mode of life. He thinks that if an Ammosates were to become sexually mature and degenerate still further, forms would result which would resemble Amphioxus, and ultimately, if the process of degeneration went far enough, larval ascidians. Amphioxus therefore might well be considered an extremely simplified and degenerate cyclostome, and the ascidian larva the last term of this degeneration series. Both Amphioxus and the ascidians would accordingly be descended from fish, instead of fish being evolved from them. Dorn conceived that the transformation of the annelid into the vertebrate took place mainly by reason of an important transforming principle, which he calls the principle of function change. Each organ, Dorn thinks, has besides its principal function a number of subsidiary functions which only await an opportunity to become active. The transformation of an organ takes place by reason of the succession of the functions which one and the same organ possesses. Each function is a resultant of several components, of which one is the principal or primary function, while the others are the subsidiary or secondary functions. The weakening of the principal function and the strengthening of a subsidiary function alters the total function, the subsidiary function gradually becomes the chief function, the total function becomes quite different, and the consequence of the whole process is the transformation of the organ, p. 60. Examples of function change are not difficult to find. Thus the stomach in most vertebrates performs both a chemical and a mechanical function, but in some forms a part of it specializes in the mechanical side of the work and becomes a gizzard, while the remaining part confines its energies to the secretion of the gastric juice. So, too, it is through function change that certain of the ambulatory appendages of arthropods have become transformed into jaws. Their function as graspers of food has gradually prevailed over their main function as walking limbs. In the evolution of vertebrates from annelids, the principle came into action in many connections: in the formation of a new mouth from gill slits, in the transformation of gills into fins and limbs, of segmental organs into gill slits, and so on. Dorn tells us that the principle of function change was suggested to him by Mivart's Genesis of Species, 1870, and he points out how it enables a partial reply to be made to the dangerous objection raised against the theory of natural selection that the first beginnings of new organs are necessarily useless in the struggle for existence. We may note in passing that a somewhat similar idea was later applied by Kleinenberg to the explanation of some of the ancestral features of development. He pointed out in his classical memoir on the embryology of the annelid Lopodorhynchus 400 that many embryonic organs seem to be formed for the sole purpose of providing the necessary stimulus for the development of the definitive organs. Thus the notochord is the necessary forerunner of the vertebral column, cartilage the precursor of bone. From this point of view, he writes, many rudimentary organs appear in a different light. Their obstinate reappearance throughout long phylogenetic series would be hard to understand were they really no more than reminiscences of bygone and forgotten stages. Their significance in the processes of individual development may in truth be far greater than is generally recognized. When in the course of the phylogeny they have played their part as intermediary organs, Vermittelungsorgane, they assume the same function in the ontogeny. Through the stimulus or by the aid of these organs, now become rudimentary, the permanent parts of the embryo appear and are guided in their development. When these have attained a certain degree of independence, the intermediary organ, having played its part, may be placed upon the retired list. 401 Dorn was well aware of the functional, or as he calls it, the physiological, orientation of his principle, and he rightly regarded this as one of its chief merits. He held that morphology became too abstract and one-sided if it disregarded physiology completely. He saw clearly that the evolution of function was quite as important a problem as the evolution of form, and that neither could be solved in isolation from the other. The concept of function change is purely physiological, he writes. It contains the elements out of which perhaps a history of the evolution of function may gradually arise, and for this very reason it will be of great utility in morphology, for the evolutionary history of structure is only the concrete projection of the content and course of the evolution of function, and cannot be comprehended apart from it. p. 70. 402 It is very instructive in this connection to note that Dorn was not, like so many of his contemporaries, a dogmatic materialist, but upheld the common-sense view that vital phenomena must, in the first instance at least, be accepted as they are. It is for the time being irrelevant, he writes, to squabble over the question as to whether life is a result of physico-chemical processes or an original property, qualitat, of all being. Let us take it as given, p. 75. Semper's speculations on the genetic affinity of articulates and vertebrates are contained in two papers 403 which appeared about the same time as Dorn's. He openly acknowledges that his work is essentially a continuation of Geoffroy's transcendental speculations, and gives in his second paper a good historical account of the views of his great predecessor. It is a significant fact that evolutionary morphologists very generally held that Geoffroy was right in maintaining against Cuvier 404 the unity of plan of the whole animal kingdom, for they saw in this a strong argument for the monophyletic descent of all animals from one common ancestral form. In his first paper Semper does little more than break ground. He insists on the fact that both annelids and vertebrates are segmented animals, and he points out how close is the analogy between the nephridia or segmental organs of the former and the excretory, mesonephric, tubules of the latter, upon which he published in the same volume an extensive memoir. At this time he considered balanoglossus by reason of its gill slits, its notochord he did not know, to be the nearest living representative of the ancestral form of vertebrates and annelida. His second paper is a more exhaustive piece of work and deals with every aspect of the problem, both from an anatomical and from an embryological standpoint. It is consciously and admittedly an attempt to apply Geoffroy's principle of the unity of plan and composition to the three great metameric groups, the annelida, arthropoda, and vertebrata. Semper follows Geoffroy's lead very closely in maintaining that it is not the position of the organs relative to the ground that must be taken into account in establishing their homologies, but solely their spatial relations one to another. He holds that dorsum and venter are terms of purely physiological import, and he proposes to substitute for them the terms neural and cardial, better, hemal, surfaces, either of which may be either dorsal or ventral in position. Having established this primary principle, Semper has little difficulty in showing that the main organs of the body lie to one another in the same relative positions in annelida, arthropoda, and vertebrata, and this, together with the metameric segmentation common to them all, constitutes his first great argument in favor of their genetic relationship. But he has still to show that annelids possess at least the rudiments of certain organs which seem to be peculiar to vertebrates, as the gill slits, the notochord, and a nervous system developed from the ectoderm of the dorsal surface. He takes particular cognizance also of the old distinction drawn by von Baer, that vertebrates show a double symmetrical mode of development, evolutio bigemina, the dorsal muscle plates forming a tube above the notochord, the ventral plates a tube below the notochord, whereas articulates do not possess this axis, and form only one tube, namely, that round the vegetative organs, evolutio gemina. Semper is at pains to prove that evolutio bigemina is characteristic also of annelidan development. Fig 14 transverse section, inverted, of the worm Nys. After Semper, AC alimentary canal. SPG spinal ganglion. DP neural muscle plate. NC nerve cord. N note cord. VP hemal muscle plate. He gets his facts from an elaborate study of the process of budding in the nadi, making the somewhat risky assumption that regeneration takes essentially the same course as embryonic development. He succeeds in showing to his own satisfaction at least that in the formation of new segments in Nys and Ketogaster a strand of cells appears between the alimentary canal and the nerve cord, and that from this axial strand the hemal muscle plates grow out dorsally round the alimentary canal and the neural muscle plates ventrally round the nerve cord, see Fig 14. This strand of cells, he concludes, must clearly be the notochord, and the type of development is obviously the double symmetrical met with invertebrates. The nervous system Semper found to develop in the buds of Nys and Ketogaster by an ectodermal thickening, just as in some vertebrates. The cerebral ganglion was formed by the ends of the nerve cord growing up round the esophagus and fusing with the paired sense plates which develop from the ectoderm of the head. The cerebral ganglion is accordingly only secondarily hemal in position, and there is no need therefore to seek invertebrates for the homologue of the esophageal chamazours of annelids, as, for instance, Schneider did. Since the mouth opens on the neural surface in annelids and on the hemal surface in vertebrates, Semper considers that they cannot be equivalent structures, and he finds the homologue of the vertebrate mouth in a little pit on the hemal surface of the head in the leech clepsyn, also in the true mouth of Turbellaria and the proboscis opening in Nemertines. The primitive annelid mouth, however, does not appear in the embryogeny of vertebrates, for the great development of the brain crowds it out of existence. The homologues of the gill slits Semper finds in two little canals in the head of Ketogaster, which open from the pharynx to the exterior. In Sabellids he describes an elaborate system of gill canals, with a supporting cartilaginous framework which forms a real chimencorb or gill basket, comparable with that of Amphioxus. Gill slits, notochord, relation of nervous system, mesonephric tubules, are thus common to annelids and vertebrates. What further proof could one desire of the close relationship of these groups? Yet Semper enters into refinements of comparison, seeing, for instance, in the lateral portions of the ventral ganglia, Fig 14, SPG, the homologues of the spinal ganglia of vertebrates, and comparing the lateral line of sense organs in annelids with the lateral line in anamnia. He will not admit that Amphioxus and the ascidians show a closer resemblance to vertebrates than his beloved annelids. Amphioxus, he thinks, is not a vertebrate, and ascidians, though sharing with annelids the possession of a notochord, gill slits, and a dorsal nervous system, yet are further removed from vertebrates than the latter by reason of their lacking that essential characteristic of vertebrates, metameric segmentation. Not content with establishing the unity of plan of annelids, arthropods, and vertebrates, Semper tries to link on the annelids, as the most primitive group of the three, to the unsegmented worms, and particularly to the Turbellaria. His speculations on this matter may be summed up somewhat as follows: the common ancestor of all segmented animals is a segmented worm-like form, not quite like any existing type, resembling the Turbellaria in having two nerve strands on the dorsal side and no esophageal ring, potentially able to develop either the vertebrate or the annelid mouth, and so to give origin both to the articulate and to the vertebrate series. The common ancestor alike of unsegmented worms and of all segmented types is probably the trochosphere larva, which in the vertebrates is represented by the simple chiomblase or blastula. The annelid theory of Dorn and Semper was perhaps not so widely accepted as the rival ascidian theory, but it counted not a few adherents and gave a certain stimulus to comparative morphology. F. M. Balfour, who pointed out about the same time as Semper the analogy between the nephridia of annelids and the mesonephric tubules of vertebrates 405 while not accepting the actual theories of Dorn and Semper, took up a distinctly favorable attitude to the general idea that annelids and vertebrates were descended from a common segmented ancestor. Discussing this question in his classical work on the development of elasmobranch fishes 406, Balfour came to the conclusion that we must look for the ancestors of the Chordata, not in allies of the present Chaetopoda, but in a stock of segmented forms descended from the same unsegmented types as the Chaetopoda, but in which two lateral nerve cords, like those of Nemertines, coalesced dorsally instead of ventrally to form a median nervous cord. This group of forms, if my suggestion as to their existence is well founded, appears now to have perished. 407 He held that while there was much to be said for the interchange of dorsal and ventral surfaces postulated by Dorn and Semper, the difficulties involved in the supposition were too great. He preferred, therefore, to assume that the present vertebrate mouth was primitive, and not a secondary formation. His views as to the phylogeny of the Chordata and the genetic relation of the various classes to one another are exhibited in the following schema: 408 names of hypothetical groups being printed in capitals, names of degenerate groups in italics. The hypothetical ancestral forms, Protochordata, possessed a notochord, a ventral suctorial mouth and numerous gill slits, and were presumably descended from the common ancestor of annelids and vertebrates. Amphioxus and the ascidians found their place in the schema as degenerate offshoots of the ancestral protochordates, while the cyclostomes were in the same way the degenerate modern representatives of the ancestral protovertebrates. Balfour's suggestion, that the nervous system in annelids and vertebrates might have arisen by the dorsal or ventral coalescence of the lateral nerve cords found in their common ancestor, bore fruit in the speculations of Huebrecht 409 on the relation of Nemertines to vertebrates. The annelid theory was firmly supported by Isaac, who in his elaborate monograph on the capitellity 410 maintained against Furbringer the genetic identity of the annelidan nephridia with the kidney tubules of vertebrates. The independent discovery by E. Meyer 411 and J. T. Cunningham 412 of an internal segmental duct in Lanus, into which several nephridia opened, seemed to strengthen this view. Following Ehlers 413, Isaac found the homologue of the notochord in the accessory intestine of the capitellity and unicyte, which he supposed might easily be transformed, according to the principle of function change, from a respiratory to a supporting organ. He finally disposed of the alternative notion that the notochord was represented in annelids by the giant fibers or neurochordal strands which lie close above the nerve cord, a view held by Kowalewski 414 and for a time by Semper. These strands were shown by Isaac, and by Spengel, to be the neurolemur sheaths of thick nerve fibers which had in many cases degenerated. The view that the content of the neurochordal tubes was nervous in nature was first promulgated by Leydig in 1864. Much difference of opinion reigned as to the true homologies of the brain and mouth of annelids and vertebrates. Beard 415 and others got over the difficulty of the hemal position of the cerebral ganglion in annelids by supposing that it degenerated and disappeared altogether in the annelidan ancestor of vertebrates, and that accordingly it had no homologue in the vertebrate nervous system. Beard put forward also the ingenious theory that the hypophysis represents the old annelidan mouth. Van Beneden and Julin 416 assumed that in the ancestors of vertebrates the esophagus shifted forward between the still unconnected lobes of the brain to open on the hemal surface. The fundamental assumption of the annelid theory, that dorsal and ventral surfaces are morphologically interchangeable, seemed rather bold to many zoologists, and Gegenbohr 417 voiced a common opinion when he rejected as unscientific the comparison of the ventral nerve cord of articulates with the dorsal nervous system of vertebrates. The balanoglossus theory of vertebrate descent also belongs, at least in its first form, to the earlier group of evolutionary speculations. The gill slits of balanoglossus were discovered by Kovalevsky as early as 1866. 418 Tornaria was discovered by J. Muller in 1850, but by him considered an asterid larva. Its true nature as the larva of balanoglossus was made out by Metchnikoff in 1870, who also remarked upon its extraordinary likeness to the larvae of echinoderms. 419 That it had some relationship with vertebrates was recognized by Semper, Gegenbohr, and others, but the full working out of its vertebrate affinities is due to Bateson. 420 Bateson broke completely with the Dorn-Semper view that the metamerism of articulates and vertebrates must be put down to inheritance from a common ancestor. He held that metamerism was merely a special manifestation of the general property of repetition, common to all living things, cf. Owen's vegetative force, and that accordingly, however far back a segmented ancestor of a segmented descendant may possibly be found, yet ultimately the form has still to be sought for in which these repetitions had their origin. P. 549. The meaning of the phenomenon was obscure, but he was convinced that the explanation was not to be found in ancestry. This much alone is clear, he wrote, that the meaning of cases of complex repetition will not be found in the search for an ancestral form, which, itself presenting the same character, may be twisted into a representation of its supposed descendant. Such forms there may be, but in finding them the real problem is not even resolved a single stage, for from whence was their repetition derived? The answer to this question can only come in a fuller understanding of the laws of growth and of variation, which are as yet merely terms, pages 548-9. It was in following up this line of thought that Bateson produced his monumental Materials for the Study of Variation, 1894. He found a strong positive argument for his theory that vertebrates are descended from unsegmented forms in the fact that the notochord arises as an unsegmented structure. With the notochord he homologized the supporting rod in the proboscis of balanoglossus, which like the notochord arises from the dorsal wall of the archenteron, and has a vacuolated structure. The gill slits of balanoglossus, with their close resemblance in detail to those of Amphioxus, Bateson also used as an argument in favor of the phylogenetic relationship of the Enteropneusta and Vertebrata, together with the formation from the ectoderm of a dorsal nerve tube. Bateson's views attracted considerable attention, and were thought by many to lighten appreciably the obscurity in which the origin of vertebrates was wrapped. Thus Lancaster wrote in his article on vertebrates 421 in the Encyclopaedia Britannica, it seems that in balanoglossus we at last find a form which, though no doubt specialized for its burrowing sand life, and possibly to some extent degenerate, yet has not to any large extent fallen from an ancestral eminence. The ciliated epidermis, the long worm-like form, and the complete absence of segmentation of the body muscles lead us to forms like the Nemertines. The great proboscis of balanoglossus may well be compared to the invaginable organ similarly placed in the Nemertines. The collar is the first commencement of a structure destined to assume great importance in cephalochorda and craniata, and perhaps protective of a single gill slit in balanoglossus before the number of those apertures had been extended. Borrowing, as we may, the nephridia from the Nemertines, and the lateral in addition to the dorsal nerve, we find that balanoglossus gives the most hopeful hypothetical solution of the pedigree of vertebrates. Much doubt was cast upon the chaudate affinities of the Enteropneusta by Spengel in his monograph of the group 422, but when the development of the chylome came to be more thoroughly worked out in balanoglossus and Amphioxus, The striking resemblance in this respect between the two forms gave additional support to the Batesian view. 423-386. The stages in the development of microscopical technique are well summarized by R. Burkhardt, Geschichte Zoologie, p. 121, Leipzig 1907. 387. Entwicklungsgeschichte Amphioxus lanceolatus, MEM. Akademik St. Petersburg, Petrograd, 7, 11, No. 4, 1867, 17 pages, 3 PLS 388. Weitere Studie an die Entwicklungsgeschichte Amphioxus lanceolatus, Arch für Micro. Anat, 13, pages 181 to 204, 1877. 389. Particularly by Hatschek, 1881, and Bovary, 1892. 390. Entwicklungsgeschichte Einfachen Acidien, MEM. Akademik St. Petersburg, Petrograd, 7, X, No. 15, 1866, 19 pages, 3 PLS. Weitere Studie an die Entwicklung der Einfachen Acidien, Arch F. Micro. Anat, 7, pages 101 to 130, 1871. 391. Descent of Man, I, p. 205, 1871. 392. Arch F. Micro. Anat, 6, 1870, and 8, 1872. 393. Archives de Biologie, 1884, 1885, and 1887. 384. Bull. Akademik St. Petersburg, Petrograd, 13, 1869, and Zeitz. F. Wiss. Zoll, XXII, 1872. 395. MEM. Akademik St. Petersburg, Petrograd, 7, 19, 1873. 396. Jard, Archzoologie Expert. Gen. I, 1872, and Lacazzi Duthiers, Ibid, 3, 1874. 397. For the later history of the Amphioxus acidian theory, the reader may be referred to A. Wiley's well-known work, Amphioxus and the Ancestry of the Vertebrates, New York and London, 1894, and to Delagy T. Héroard, Traité de zoologie concrète, tome 8, Paris, 1898. 398. Studie an zur Urgeschichte der Wirbeltierkörpers, Midheil. Zoll Stat Nepal, 1882-1907. 399. Leidig, vom Baude Theorischen Körpers, Tübingen, 1864, who, in a measure, forestalled Dorn and Semper by comparing vertebrates with reversed arthropods, specially insects, supposed the old mouth to pass between the crura cerebri. 400. Zeitz. F. Wiss. Zoll, Sliv, 1886. 401. Quoted by E. B. Wilson, Woods Hole Biological Lectures for 1894, p. 121. 402. C. F. Metchnikoff, Quart. Journ. Microsk. Sci. XXIV, pages 89 to 111, 1884. 403. Die Stammesverwandtschafter Wirbeltier und Wirbellosen, Arb. Zoologie Zoot Institut. Würzburg, 2, pages 25 to 76, 1875, Die Verwandtschaftsbeziehungen der Gegliederten Tiere, Ibid. 3, pages 115 to 404, 1876 to 7. 404 Abuse of Cuvier also dates from the early days of evolution, see Radl, 2, pages 12 to 17. 405 On the Origin and History of the Urinogenital Organs of Vertebrates, Journ. Anat Physical, X, 1876. The conclusions of Balfour and Semper were adversely criticized by M. Furbringer, Morphology, 4, 1878, and were negatived by later research. 406 A monograph on the development of elasmobranch fishes, London, 1878. 407 A treatise on comparative embryology, Volume 2, p. 311, London, 1881. 408 LOCCIT, Volume 2, p. 327. 409 On the ancestral form of the Chordata, QJMS, XXIII, 1883. The relation of the Nemertea to the Vertebrata, Ibid, XXVII, 1887. Huebrecht gives the credit for the first indication of the relationship of Nemertines and vertebrates to Harding, Leerboek van de Grondbeginselender Dierkunde, 1874. 410 Monographie der Kapitäliten de Golfies van Nepal, Fauna u Flora de Golfies van Nepal, Monig. 16, Berlin, 1887. 411 Mit. Zoel Stat Nepal, 7, 1887. 412 Nature, 30, p. 162, 1887. 413 Nebendarmuende Corda dorsalis, Nacre. Guess. Wis. Göttingen, p. 390, 1885. 414 Embryologisk Studien en Wormer nu Arthropoden, MEM. Academici St. Petersburg, Petrograd, 7, 16, 1870. And in Arch F. Micro. Anat, 7, p. 122, 1871. 415 The Old Mouth and the New, Anat Ans, 3, 1888. Nature, 36, 1889. 416 Recherches sur la morphologie de Tunis Arch de Bile, 6, 1887. 417 Die Stellung Bedeutung der Morphologie, Morphjarb, I, pages 1 to 19, 1876. 418 Anatomie de Balanoglossus, MEM. Academici St. Petersburg, Petrograd, 7, x, 1866. 419 Zeit. F. Wis. Zoel, XX, 1870. For a recent view of the relation of the Enteropneusta to the Echinoderma, see J. F. Gemmill, Philosophy Transaction B, CCV, pages 213 to 94, 1914. 420 In a series of papers published in 1884 to 6, the speculative results being discussed in his memoir on the ancestry of the Chordata, QJMS, NS, XXVI, pages 535 to 71, 1886. 421 Reprinted in Zoological Articles, London, 1891. 422 Die Enteropneusen de Golfes von Nepal, Fauna und Flora de Golfes von Nepal, Monig. 18, Berlin, 1893. 423 C. McBride, a review of Professor Spengel's monograph on Balanoglossus, QJMS, 30, 1894, and the early development of Amphioxus, QJMS, XL, 1898. Chapter 16 The Germ Layers and Evolution in his papers of 1866 and 1867 Kovalevsky had remarked upon the widespread occurrence of a certain type or fundamental plan of early embryonic development, characterized by the formation, through invagination, of a two-layered sac, whose cavity became the alimentary canal. This developmental archetype was manifested in, for instance, Sagitta 424, Rana 425, Limnia 426, Astacus 427, Pharaones 428, Asterias 429, Acidia 428, the Ctenophora 428 and Amphioxus 428. He noticed also that the invagination opening often became the definitive anus. Further instances of this mode of development were later observed by Metchnikoff 430 and by Kovalevsky 431 himself, but it was left to Haeckel to generalize these observations and build up from them his famous gastria theory. This was first enunciated in his monograph of the calcareous sponges 432 and worked out in detail in a series of papers published in 1874-76. 433 Haeckel maintained that the gastrula stage occurred in the development of all metazoa, and that it was typically formed, by invagination, from a hollow sphere of cells or blastula. This typical formation might be masked by xenogenetic modifications caused chiefly by the presence of yolk. The gastrula stage was the palingenetic repetition of the ancestral form of all metazoa, the gastria. From the gastria theory there followed at once two consequences: 1. That ectoderm and endoderm, invagination cavity, erdarm, and gastrula mouth, ermand or protostoma, were, with all their derivatives, homologous, because homogeneous, throughout the metazoa, and, 2, that the descent of the metazoa had been monophyletic, since all were derived from the ancestral gastria. Huxley's suggestion, supra, p. 208, that the outer and inner layers in coelentra were homologous with the ectoderm and endoderm of the germ was thus fully confirmed and greatly extended. The great importance of the gastria theory lay in the fact that it linked up, by means of the biogenetic law, the germ layer theory with the doctrine of evolution. It supplied an evolutionary interpretation of the earliest and most important of embryogenetic events, the process of layer formation. Upon the gastria theory or its implications were founded most of the phylogenetic speculations which subsequently appeared. Upon the gastria theory Haeckel based a system of phylogenetic classification which was intended to replace Cuvier's and von Bayer's doctrine of types. This took the form of a monophyletic ancestral tree. Its main outlines are given on p. 290 in graphic form, combined and modified from the table on p. 53 of the 1874 paper and the genealogical tree given in the Koswama 434 monophyletic genealogical tree of the animal kingdom, based upon the gastria theory and the homology of the germ layers. The scheme is in many respects an interesting and important one. The great contrast between the protozoa, or animals with neither gut nor germ layers, and the metazoa, which possess both structures, is for the first time clearly brought out. The derivation of all the metazoa from a single ancestral form, the gastria, leads to the conclusion that the types are not distinct from one another as Cuvier and von Baer supposed, but agree in the one essential point, in the possession of an archenteron, Lancaster, 1875, and an ectoderm and endoderm which are homologous throughout all the metazoan phyla. Finally, in the separation of the sponges, Coelenterata and Achylomi as animals lacking a body cavity or chylome 435 from the four higher phyla, which are essentially Chylomatidae, there is contained the germ of a conception which later became of importance. Somewhat similar views as to the importance of the germ layer theory for the phylogenetic classification of animals were published by Sir E. Ray Lankester in 1873. 436 He distinguished three grades of animals: the Homoblastica, Diploblastica, and Triploblastica. The first included the Protozoa, the second the Coelenterata, the third the other five phyla, distinguished by the possession of a third layer, the mesoderm, and a blood-lymph cavity enclosed therein. He used the germ layer theory to prove the essential unity of type of all the Triploblastica. The Gastria theory gave point and substance to the biogenetic law, and enabled Haeckel to state much more concretely the parallelism existing between ontogeny and phylogeny. He was able to assert that five primordial stages, each representing a primitive ancestral form, recurred with regularity in the very earliest development of all metazoa. 437 These were the Monrula, Scitula, Morula, Blastula, and Gastrula, see Fig 15. The Monrula was the fertilized ovum after the disappearance of the germinal vesicle. 438 It was the equivalent of the primordial anucleate monera, which are the ancestors of all animals. Fig 15 The five primary stages of ontogeny. After Haeckel: 1 Monrula, 2 Scitula, 3 Morula, 4 Blastula, 5 Gastrula. The ovum after the nucleus had been reformed became the Scitula, which was the ontogenetic counterpart of the amoeba. The Morula, a compact mulberry-like congeries of segmentation cells, corresponded to the Cynamoeba, or earliest association of undifferentiated amoeboid cells to form the first multicellular organism. The Blastula, or hollow sphere of segmentation cells, usually ciliated, was reminiscent of the Plania, an ancestral free-swimming form whose nearest living relation is the spherical Magosphera. The Gastrula, finally, is the two-layered sac formed from the Blastula, typically by invagination of its wall. It repeats the organization of the Gastria, which is the common ancestor of all metazoa, and finds its nearest living counterpart in the simple sponges Halophisma and Gastrophisma. 439 The ancestral line of all the higher animals begins with the five hypothetical forms of the Moneran, Amoeba, Cynamoeba, Plania, and Gastria. We may take the following account 440 of the phylogeny of the human species, from the Gastria stage onwards, as typical of Haeckel's speculations on the evolution of the higher forms. The progenitors of man are, after the Gastrida 1. Turbellaria. * 2. Scolecida. Worms with a chylome, probably represented at the present day by Balanoglossus. * 3. Hematiga. Evolved from Scolecida by formation of dorsal nerve tube and chorda, and resembling tailed larvae of ascidians. 4 Acrania. With metameric segmentation, including Amphioxus. 5 Monorhina. Cyclostomes. 6 Selachia. 7 Dipnosta. 8 Zozobranchia. Amphibia with permanent gills. 9 Sogera. Tailed amphibia. * 10. Protomnia. * 11. Promammalia. 12 Marsupialia. 13 Prosimii. 14 Manocerca. Tailed apes. 15 Anthropoids. 16 Pithecanthropi. 17 Homines. It will be noticed that except for the hypothetical forms, marked with an asterisk, which are themselves generalist classificatory groups, the ancestral forms belong to long recognized classes. the whole course of the evolution follows well-worn systematic lines. This is typical of Haeckel's phylogenetic speculations. A more abstractly morphological scheme of the evolution of vertebrates is given in the Systematic Phylogeny of 1895. 441. The ontogenetic and ancestral stages are arranged in parallel columns, thus Cytula, Cytia, Protozoa, Morula, Moria, Synobium of Protozoa, Blastula, Blastia, Volvochina, etc. Depula, invaginated Blastula, Dipia, Gastrula, Gastria, cf. Olynthus, Hydra, and primitive Coelentra. Chilomula, with one pair of chilome pockets. Chilomia, cf. Sagitta, Acidia, and primitive Helminthus. Chaudula, with medullary tube and chorda. Cordia, cf. Ascidion larva and larva of Amphioxus. Spondula, with segmented mesoderm. Prospondylus, primitive vertebrate. This scheme differs from the earlier one chiefly in taking into account certain advances, notably as regards the cytology of the fertilized ovum and the true nature of the chylome, which had been made in the interval of some 20 years. Haeckel's Gastria theory, though it exercised a great influence upon the subsequent trend of phylogenetic speculation, was by no means universally accepted telle quel. Opinions differed considerably as to the primitive mode of origin of the two-layered sac, which was very generally admitted to be of constant occurrence in early embryogeny. Ray Lancaster, in his paper of 1873, and more fully in 1877 442, propounded a planula theory, according to which the ancestral form of the metazoa was a two-layered closed sac formed typically by delamination, less often by invagination. He denied that the invagination opening, which he named the blastopore, represented the primitive mouth. 443, holding that this was typically formed by an inruptive process at the anterior end of the planula, which led to the formation of a stomadeum. A similar process at the posterior end gave rise to the anus and the proctodeum. The question as to whether delamination or invagination was to be considered the more primitive process was discussed in detail by Balfour. 444, without, however, any very definite conclusion being reached. He held that both processes could be proved in certain cases to be purely secondary or adaptive, and that accordingly there was nothing to show that either of them reproduced the original mode of transition from the protozoa to the ancestral two-layered metazoa, p. 342. He by no means rejected the theory that the gastria, however evolved, was a primitive form of the metazoa, but, having regard to the great variations shown in the relation of the blastopore to mouth and anus, pages 340-1, he was inclined to think that if the gastrula had any ancestral characters at all, these could only be of the most general kind. Balfour's attitude perhaps best represents the general consensus of opinion with regard to the gastria theory. From the same origins as the gastria theory arose the theory of the chylome. The term dates back to Haeckel in 1872, and the observations which first led up to the theory were made by the men who supplied the foundations of the gastria theory: Agassiz, Metchnikoff, and Kovalevsky. But it was not Haeckel himself who enunciated the chylome theory. It will be remembered that Remak introduced in 1855 the conception of the mesoderm as an independent layer derived from the endoderm. The pleuroperitoneal or body cavity was formed as a split in the ventral plates of the mesoderm. Haeckel's chylome corresponded to the pleuroperitoneal cavity of Remak, but his view of the origin of the mesoderm brought him much closer to von Bayer's conception of the origin of two secondary layers from ectoderm and endoderm respectively than to Remak's conception of the mesoderm as a single independent layer. Much uncertainty reigned at the time as to the exact manner of origin of the mesoderm. 445 Some held that it developed from the ectoderm, others that it originated in the endoderm, while still others, and among them Haeckel, considered that part of it came from the ectoderm and part from the endoderm, pages 23 to 4, 1874. The solution of the problem came from those observations on the development of the lower forms to which we have just alluded. The early history of these discoveries and of the theory which grew out of them has been well summarized by Lancaster 446 and may conveniently be given in his own words as far back as 1864. Alexander Agassiz, Embryology of the Starfish, in Contributions to the Natural History of the United States, Volume V, 1864, showed in his account of the development of echinoderma that the great body cavity of those animals developed as a pouch-like outgrowth of the archenteron of the embryo, whilst a second outgrowth gave rise to their umbilical system, and in 1869 Metchnikoff, MEM de l'Académique Impériale des Sciences de St. Petersburg, Series 7, Volume 14, 1869, confirmed the observations of Agassiz, and showed that in Tornaria, the larva of Balanoglossus, a similar formation of body cavities by pouch-like outgrowths of the archenteron took place. Metchnikoff has further the credit of having, in 1874, Zeitgeist. Zoology, Volume XXIV, p. 15, 1874, revived Lookert's theory of the relationship of the coelenteric apparatus of the enterocylla to the digestive canal and body cavities of the higher animals. Lookert had in 1848 maintained that the alimentary canal and the body cavity of higher animals were united in one system of cavities in the enterocylla, Verwandtschaftsverhältnisse Wirbellosenthera, Brunswick, 1848. Metchnikoff insisted upon such a correspondence when comparing the echinoderm larva, with its still continuous enteron and chylome, to a ctenophore, with its permanently continuous system of cavities and canals. Kowalovsky, in 1871, showed that the body cavity of Sagitta was formed by a division of the archenteron into three parallel cavities, and in 1874 demonstrated the same fact for the Brachiopoda. In 1875, Quart. Journ. MICR. Sci. Volume 15, p. 52, Huxley proposed to distinguish three kinds of body cavity: the schizocele, formed by the splitting of the mesoblast, as in the chick's blastoderm; the enterocoel, formed by pouching of the archenteron, as in echinoderms, Sagitta and Brachiopoda; and the epicoel. Immediately after this I put forward the theory of the uniformity of origin of the chylome as an enterocoel, Quart. Journ. MICR. Sci. April, 1875. My theory of the chylome as an enterocoel was accepted by Balfour and was greatly strengthened by his observations on the derivation of both notochord and mesoblastic somates from archenteron in the elasmobranchs, and by the publication in 1877 by Kowalovsky of his second paper on the development of amphioxus, in which the actual condition which I had supposed to exist in the vertebrata was shown to occur, namely, the formation of the mesoblast as paired pouches in which a narrow lumen exists, but is practically obliterated on the nipping off of the pouch from the archenteron, after which process it opens out again as chylome, pages 16 to 18. The enterocylic theory was taken up by O. and R. Hertwig as an essential part of their chylome theory 447. In a lengthy series of monographs these workers made a comparative study of the mode of formation of the middle layer, and arrived at a coherent theory of its origin. They distinguished in the middle layer two quite distinct elements: the mesoblast proper, formed by the evagination of the walls of the archenteron, and the mesenchyme, formed by free cells buddied off from the germ layers. The following passage gives a good idea of their views and of the phylogenetic implications involved. Ectoblast and entoblast are the two primary germ layers which arise from the invagination of the blastula, they are always the first to be laid down, and they can be directly referred back to a simple ancestral form, the gastria. They form the limits of the organism towards the exterior and towards the archenteron. The parietal and visceral mesoblast, or the two middle layers, are always of later origin, and arise through evagination or plating of the entoblast, the remainder of which can now be distinguished as secondary entoblast from the primary. They form the walls of a new cavity, the enterocoel, which is to be regarded as a nipped off diverticulum of the archenteron. Just as the two-layered animals can be derived from the gastria, so can the four-layered animals be derived from a chylome form. Embryonic cells, which become singly detached from their epithelial connections, we consider to be something quite different from the germ layers, and accordingly we call them by the special name of mesenchyme germs or primary cells of the mesenchyme. They may develop both in two-layered and in four-layered animals. Their function is to form between the epithelial limiting layers a secreted tissue, secretgebe, or connective tissue with scattered cells, which cells can undergo, like the epithelial elements, the most varied modifications. This secreted tissue in its simple or in its differentiated state, with all its derivatives, we call the mesenchyme, p. 122. The important point for us is that, just as all metazoa were considered by Haeckel to be descended from the gastria, so all chylometi were held by the Hertwigs to be derived from an original chylomete form. In both cases an embryological archetype becomes a hypothetical ancestral form. The chylome theory was considerably modified, extended, and developed by later workers, particularly as regards the relations to the chylome of the genital organs and ducts and the nephridia, but no special methodological interest attaches to these further developments. 448 We shall here focus attention upon one interesting line of speculation followed out in this country particularly by Sedgwick, the theory of the actinozoan ancestry of segmented animals. Its relation to the chylome theory lies in the fact that Sedgwick regarded the segmentation of the body as molded upon the segmentation of the mesoblast, which in its turn, as Kovalevsky and Hatschek had shown, was a consequence of its mode of origin as a series of pouches of the archenteron. In other respects Sedgwick's speculations link on more closely to the gastria theory, for one of his main contentions is that the blastopore or ermine is homologous throughout at least the three metameric phyla. In following up Balfour's observations on the development of Peripatus 449, Sedgwick was struck with the close resemblance existing between the elongated slit-like blastopore of this form, giving rise to both mouth and anus, with its border of nervous tissue, and the slit-like mouth of the actinozoan, functioning both as mouth and anus, round which, as the Hertwigs had shown, there lies a special concentration of nerve cells and nerve fibers. He found another point of resemblance in the gastric pouches of the actinozoa, which he homologous directly with the enterocoelic pouches of the chylometi. He was led to enunciate the following theses: 450, 1. That the mouth and anus of vermes, mollusca, arthropoda, and probably vertebrata, is derived from the elongated mouth of an ancestor resembling the actinozoa. 2. That zoomets are derived from a series of archenteric pouches, like those of actinozoa and medusae. 3. That excretory organs, nephridia, segmental organs, are derived from parts of these pouches which in the ancestral form, as in many polyps, were connected by a circular or longitudinal canal, and open to the exterior by pores. This longitudinal canal was lost in invertebrates, but persisted in vertebrates as the pronephric duct, while the pores remained in invertebrates and disappeared in vertebrates. 4. That the tracheae of arthropods, as well as the canal of the central nervous system in vertebrates, are to be traced back to certain ectodermal pits in the diploblastic ancestor comparable to the subgenital pits of the Siphomegaceae. These ectodermal pits were all originally respiratory organs. The essence of all these propositions, he writes, lies in the fact that the segmented animals are traced back not to a triploblastic unsegmented ancestor, but to a two-layered coelenterate-like animal with a pouched gut, the pouching having arisen as a result of the necessity for an increase in the extent of the vegetative surfaces in a rapidly enlarging animal, for circulation and respiration, p. 47. I have attempted to show, he writes further on, that the majority of the triploblastica are built upon a common plan, and that plan is revealed by a careful examination of the anatomy of coelenterata, that all the most important organ systems of these triploblastica are found in a rudimentary condition in the coelenterata, and that all the triploblastica referred to must be traced back to a diploblastic ancestor common to them and the coelenterata, p. 68. The main assumption was that the neural or blastoporal surface must be homologous throughout the metazoa, though it was dorsal in the Chordata, ventral in the Annelida and Arthropoda. He derived the central nervous system of the Chordata from the circumoral ring of the common ancestor by means of the hypothesis that both the pre-blastoporal and the post-blastoporal parts of it disappeared. 451. The characteristic relation of the central nervous system to the blastopore in Annelida and vertebrates had already been pointed out by Kołowski. 452, who had also sketched a theory of the common descent of these two phyla from an ancestral form in which the nervous system encircled the blastopore. In 1882, before the publication of Sedgwick's papers, A. Lang 453 had put forward the somewhat similar view that the stomach diverticula of the turbellaria, which he had found to be segmentally arranged in certain trichlades, were the morphological equivalents of the enterocylic pouches of higher animals. This view, however, he soon gave up. 454. Sedgwick's views found a supporter in A.A.W. Hubrecht. 455, who utilized them in connection both with his speculations on the relation of nemertines to vertebrates, and with his exhaustive work on the early development of the mammalia. He postulated as the far-back ancestor of vertebrates, an actinia-like, vermiform being, elongated in the direction of the mouth slit, p. 410, 1906, and derived the central nervous system from the circumoral ring of this primitive form, the notochord from its stomateum, and the chylome from the peripheral parts of the gastric cavity, p. 169, 1909. 424. Gegenbohr, Zeitz. F. Wyss. Zoel, v. 1853. 425. Remak, Loccit, p. 183, pl 12. 426. Lear-Bolliot, Ansinat. 4, 18, pages 118 to 9, 1862. 427. Lear-Bolliot, in Remak, p. 183 fn 428. Kołowski, MEM. Academic Sci. St. Petersburg, Petrograd, 7, X and 11, 1866 and 1867. 429. A. Agassiz, Contribution Nat History United States, v. 1864. 430. MEM. Academic Sci. St. Petersburg, Petrograd, 7, 14, 1869. 431. Embryology. Studien and Wormer New Arthropoden, MEM. Academic Sci. St. Petersburg, Petrograd, 7, 16, 1870. 432. Die Koschwame, 3 volumes, Berlin, 1872. General chapters translated in Nmag Nat History, 4, 11, pages 241 to 62, 421 to 30, 1873. 433. Digastria Theory, Die Phylogenetische Klassifikation der Tierreichs und die Homologie der Keimblätter. Genus Zeitschrift, 8, pages 1 to 55, 1874. Die Gastrula und die Eiferchung der Tiere, Ibid, 9, pages 402 to 508, 1875. Die Physimarine, Gastrieten der Gegenart, and Nachtrage zur Gastria-Theorie, Ibid, X, pages 55 to 98, 1876. Republished in Biologische Studien, 2nd part, Studien zur Gastria-Theorie, 270 pages, 14 pls, Jena, 1877. 434 CN Mag Nat History, 4, 11, p. 253. 435 Term first introduced in Die Kosmologie, p. 468, 1872. 436 On the primitive cell layers of the embryo as the basis of genealogical classification of animals, and on the origin of vascular and lymph systems, and Mag Nat History, 4, 11, pages 321 to 38, 1873. 437 First distinguished in Die Kosmologie, I, p. 465. 438 Even in the 70s it was still believed by many that the egg nucleus disappeared on fertilization. The true nature of the process was not fully made out till 1875, when O. Hertwig observed the fusion of egg and sperm nuclei in Toxopneustes, Morphology, I, 1876. 439 Studien zur Gastria-Theorie, p. 214, 1877. These forms were known even in 1870, Carter, and Mag Nat History, 4, 6, pages 346 to 7, to be foraminifera. The figures of supposed collar cells, etc., do credit to Haeckel's imagination. 440 History of Creation, ENG Transaction, 2, pages 278 ff 441 Systematische Phylogenie, 3, p. 41, Berlin, 1895. 442 Notes on the Embryology and Classification of the Animal Kingdom, QJMS, NS, 17, pages 399 to 454, 1877. 443 It was part of the non-historic mechanism of growth, LOCCIT, p. 418. 444 Treatise on Comparative Embryology, 2, Chapter 13, 1881. For a modern discussion of this problem, see Huebrecht, QJMS, Slicks, 1906. 445 C. Balfour, LOCCIT, Chapter 13. 446 A Treatise on Zoology, pt 2, 1900. Introduction by Sir E. Ray Lancaster. 447 Studien zur Blättertheorie, Jena, 1879-80. Die Kilomtheorie, Versuch einer Erklärung der mittleren Keimblättis, Genus Zeitschrift, 15, pages 1 to 150, 1882. 448 For an historical account of this work, see Lancaster, LOCCIT, pages 21 to 37. 449 Proc Roy. SOC, 1883, and QJMS, XXIII, 1883. 450 Origin of metameric segmentation, QJMS, XXIV, pages 43 to 82 1884. 451. See further the same author's article Embryology in the Encyclopaedia British, Volume 11, 11th ed., Cambridge, 1910. 452. Arch F. Micrer. Anat, 13, pages 181 to 204, 1877. 453. Der Bau von Gunda segmentata, Myth. Zoel Stat Neep, 3, pages 187 to 250, 1882. 454. Die Polycladen, Fauna Euflora de Golfis von Nepal, Monig. V. Leipzig, 1884, and Beiträge zu einer Trophocell-Theorie, Gen. Zeitz, 38th, pages 1 to 373, 1904, which see for a modern account of theories of metamerism. 455. Die Abstammung der Anliten Daten, Gen. Zeitz, 36, pages 151 to 76, 1905. The Gastrulation of the Vertebrates, QJMS, Slicks, pages 403 to 19, 1906. Early ontogenetic phenomena in mammals, QJMS, Lyene, pages 1 to 181, 1909. Chapter 17. The Organism as an Historical Being. Of late the attempt to arrange genealogical trees involving hypothetical groups has come to be the subject of some ridicule, perhaps deserved. But since this is what modern morphological criticism in great measure aims at doing, it cannot be altogether profitless to follow this method to its logical conclusions. That the results of such criticism must be highly speculative, and often liable to grave error, is evident. The quotation is from Battison's paper of 1886, and it is symptomatic of the change which was soon to come over morphological thought. New interests, new lines of work, began to usurp the place which pure morphology had held so long. This is accordingly a convenient stage at which to take stock of what has gone before, to consider the relation of evolutionary morphology to the transcendental and the Cuverian schools of thought which preceded it, and to make clear what new element evolution theory added to morphology. The close analogy between evolutionary and transcendental morphology has already been remarked upon and illustrated in the last 3 chapters. We have seen that the coming of evolution made comparatively little difference to pure morphology, that no new criteria of homology were introduced, and that so far as pure morphology was concerned, evolution might still have been conceived as an ideal process precisely as it was by the transcendentalists. The principle of connection still remained the guiding thread of morphological work, the search for archetypes, whether anatomical or embryological, still continued in the same way as before, and it was a point of subordinate importance that, under the influence of the evolution theory, these were considered to represent real ancestral forms rather than purely abstract figments of the intelligence. The law of Meckel-Saris was revived in an altered shape as the law of the recapitulation of phylogeny by ontogeny. The natural system of classification was passively inherited, and, by a petitio principii, taken to represent the true course of evolution. It is true that the attempt was made to substitute for the concept of homology the purely genetic concept of homogeny, but no inkling was given of any possible method of recognizing homogeny other than the well-worn methods generally employed in the search after homologies. There was a close spiritual affinity between the speculative evolutionists and the transcendentalists. Both showed the same subconscious craving for simplicist conceptions. The transcendentalists clung fast to the notion of the absolute unity of type, of the ideal existence of the one animal, and the evolutionists did precisely the same thing when they blindly and instinctively accepted the doctrine of the monophyletic descent of all animals from one primeval form. Geoffroy persisted in regarding arthropods as being built on the same plan as vertebrates. Dorn and Semper did nothing different when they derived both groups from an ancestor combining the main characters of both. The determination to link together all the main phyla of the animal kingdom and to force them all into a single mold was common to evolutionary and pre-evolutionary transcendentalists alike. From the fact that all metazoa develop from an ovum, which is a simple cell, the evolutionists inferred that all must have arisen from one primordial cell. From the fact that the next step in development is the segmentation of the ovum, they argued that the ancestral metazoa came into being through the division of the primal protozoan with aggregation of the division products. From the fact that a gastrula stage is very commonly formed when segmentation has been completed, they assumed that all germ-layered animals were descended from an ancestral gastria. They quite ignored the possibility that a different explanation of the facts might be given. They seized upon the simplest and most obvious solution because it satisfied their overwhelming desire for simplification. But is the simplest explanation always the truest, especially when dealing with living things? One may be permitted to doubt it. It is easy to account for the structural resemblance of the members of a classificatory group, by the assumption that they are all descended from a common ancestral form. It is easy to postulate any number of hypothetical generalist types, but in the absence of positive evidence, such simplicist explanations must always remain doubtful. The evolutionists, however, had no such scruples. Phylogenetic method differed in no way from transcendental, except perhaps that it had learned from von Baer and from Darwin to give more weight to embryology. The criticisms passed by Cuvier and von Baer upon the transcendentalists and their recapitulation theory might with equal justice be applied to the phylogenetic speculations which were based on the biogenetic law. There was the same tendency to fix upon isolated points of resemblance and disregard the rest of the organization. Thus, on the ground of a presumed analogy of certain structures to the vertebrate notochord, several invertebrate groups, as the Enteropneusta, the Rhabdopleura, the Nemertea, were supposed to be, if not ancestral, at least offshoots from the direct line of vertebrate descent. And if other points of resemblance could in some of these cases be discovered, yet no successful attempt was made to show that the total organization of any of these forms corresponded with that of the vertebrate type. With the possible exception of the Ascidian theory, all the numerous theories of vertebrate descent suffered from this irremediable defect, and none carried complete conviction. In spite of the efforts of the evolutionists, as of those of the transcendentalists, the phyla or types remain distinct, or at best connected by the most general of bonds. The close affinity of transcendentalists and evolutionists is shown very clearly in their common contrast in habits of thought with the Cuvierian school. It is the cardinal principle of pure morphology that function must be excluded from consideration. This is a necessary and unavoidable simplification which must be carried out if there is to be a science of pure form at all. But this limitation of outlook, if carried over from morphology to general biology, becomes harmful, since it willfully ignores one whole side of life, and that the most important. The functional point of view is clearly indispensable for any general understanding of living things, and this is where the Cuvierian school has the advantage over the transcendental. Its principles are applicable to biology in general. Geoffroy and Cuvier in pre-evolutionary times well typified the contrast between the formal and the functional standpoints. For Geoffroy, form determined function, while for Cuvier function determined form. Geoffroy held that nature formed nothing new, but adapted existing materials of organization to meet new needs. Cuvier, on the other hand, was always ready to admit nature's power to form entirely new organs in response to new functional requirements. The evolutionists followed Geoffroy rather than Cuvier. They laid great store by homological resemblances, and dismissed analogies of structure as of little interest. They were singularly unwilling to admit the existence of convergence or of parallel evolution, and they held very firmly the distinctively Geoffroyan view that nature is so limited by the unity of composition that she can and does form no new organs. By no one has this underlying principle of evolutionary morphology been more explicitly recognized than by Huebrecht, who in his paper of 1887, after summarizing the points of resemblance between Nemertines and vertebrates which led him to assume a genetic connection between them, writes as follows: at the base of all the speculations contained in this chapter lies the conviction, so strongly insisted upon by Darwin, that new combinations or organs do not appear by the action of natural selection unless others have preceded, from which they are gradually derived by a slow change and differentiation. That a notochord should develop out of the archenteric wall because a supporting axis would be beneficial to the animal may be a teleological assumption, but it is at the same time an evolutional heresy. It would never be fruitful to try to connect the different variations offered, example by the nervous system throughout the animal kingdom, if similar assumptions were admitted, for there would be then quite as much to say for a repeated and independent origin of central nervous systems out of indifferent epiblasts just as required in each special case. These would be steps that might bring us back a good way towards the doctrine of independent creations. The remembrance of Darwin's, Huxley's, and Gegenbohr's classical foundations, and of Balfour's and Weismann's brilliant superstructures, ought to warn us away from these dangerous regions, p. 644. This same prejudice lies at the root of the idea of Funktionswechsel, in spite of the general functional orientation of that idea. Dorn's constant assumption is that nature makes shift with old organs wherever possible, instead of forming new ones. He derives gill slits from segmental organs, fins and limbs from gills, ribs from gill arches, and so on, instead of admitting that these organs might quite as well have arisen independently. He objects on principle to the origin of organs de novo. Thus, rebutting the suggestion that certain organs which are not found in the lower vertebrates might have arisen as new formations, he writes: against this supposition the whole weight of all those objections can be directed that are to be brought in general against the method of explanation which consists in appealing without imperative necessity to the deus ex machina, new formation, which is neither better nor worse than gene ratio equivoca, p. 21. Of a similar nature was the objection to convergence 456. Why, we may ask, were morphologists so unwilling to admit the creative power of life? Dorn, for instance, was fully aware of the great transforming influence exerted by function upon form. His theory of Funktionswechsel regards as the most powerful agent of change the activity of the animal, its effort to make the best use of its organs, to apply them at need in new ways to meet new demands. Why then did he not go a step further and admit that the animal could by its own subconscious efforts form entirely new organs? Why did most morphologists join with him in belittling the organism's power of self-transformation? The reasons seem to have been several. There is first the fundamental reason, that the idea of an active creative organism is repugnant to the intelligence, and that we try by all means in our power to substitute for this some other conception. In so doing we instinctively fasten upon the relatively less living side of organisms their routine habits and reflexes, their routine structure, and ignore the essential activity which they manifest both in behavior and in form change. We tend also to lay the causes of form change, of evolution, as far as possible outside the living organism. With Darwin we seek the transforming factors in the environment rather than within the organism itself. We fight shy of the Lamarckian conception that the living thing obscurely works out its own salvation by blind and instinctive effort. We like to think of organisms as machines, as passive inventions 457 gradually perfected from generation to generation by some external agency, by environment, or by natural selection, or what you will. All this makes us chary of believing that nature is prodigal of new organs. Other causes of the unwillingness of morphologists to admit the new formation of organs are to be sought in the main principle of pure morphology itself, that the unity of plan imposes an iron limit upon adaptation, and in the powerful influence exercised at the time by materialistic habits of thought. Teleology had become a bugbear to the vast majority of biologists, and all real understanding of the Cuvierian attitude seems, in most cases, to have been lost, although, curiously enough, teleological conceptions were often unconsciously introduced in the course of discussions on the utility of organs in the struggle for existence. Evolutionary morphology, being for the most part a form of pure or non-functional morphology, agreed then in all essential respects with pre-evolutionary or transcendental morphology. But it contained the germ of a new conception which threw a new light upon the whole science of morphology. This was the conception of the organism as an historical being. We have seen this thought expressed with the utmost clearness by Darwin himself, Supra, p. 233. In his eyes the structure and activities of the living thing were a heritage from a remote past. The organism was a living record of the achievements of its whole ancestral line. What a light this conception threw upon all biology! When we no longer look at an organic being as a savage looks at a ship as something wholly beyond his comprehension, when we regard every production of nature as one which has had a long history, when we contemplate every complex structure and instinct as the summing up of many contrivances, each useful to the possessor, in the same way as any great mechanical invention is the summing up of the labor, the experience, the reason, and even the blunders of numerous workmen, when we thus view each organic being, how far more interesting, I speak from experience, does the study of natural history become. Origin, 6th ed., pages 665-6. Sedgwick expressed the same thing from the morphological point of view when he wrote, with reference to the ancestral significance of the blastopore: if there is anything in the theory of evolution, every change in the embryo must have had a counterpart in the history of the race, and it is our business as morphologists to find it out. p. 49, 1884. By the evolution theory the problems of form were linked indissolubly with the problem of heredity. Unity of plan could no longer be explained idealistically as the manifestation of divine archetypal ideas, it had a real historical basis, and was due to inheritance from a common ancestor. The evolution theory gave meaning and intelligibility to the transcendental conception of the unity of plan. In particular, it supplied a simple and satisfying explanation of puzzling vestigial